We are going to switch gears again. We are not doing volume and area today, so we are going to do a totally different topic, slope fields. So there's two different ways to graph a differential equation. So graphing differential equations, or diffie-qs. Right, there's two methods, and we've done the first method before. You guys are like, what? Have we? So let's say we have this differential equation, dy over dx. We're going to do a simple one, cosine x. Okay? We're going to graph this in two different ways. So our method one over here, method one, this is the method that we've done before. So we separate, and you gotta integrate, right? Integrate. Yep. And then we just graph the function that we ended up with. Graph function. So here we go. We got dy is equal to cosine x dx. And then we anti-derive or integrate both sides, and we get y is equal to sine x plus c. And we know what that looks like, right? To graph that, that's pretty darn easy, right? We've got, we know sine comes up, it comes back down, it goes back up, right? So this is that pi and 2 pi. So the one that I graphed, though, was just y equals sine x, right? But this is sine x plus c. So what does that mean? We can add any number that we want, right? So this could look like this, right? So it could be like this, right? That might be sine x plus a half. And something like that. I'm not very good at it, right? And sine x plus 1. And this might be sine x minus 1, right? And it just keeps following that same curve. It just shifts up and down, right? So each pathway here is a different c. Represents a different c value. Cut off there. Okay. So that's one way to graph a differential equation, is actually solving it and then graphing. The other way that we're going to do today is the slope field. So over here, oh, we got to move back up. Here we go. Over here, we're going to do slope field, method 2. So a slope field is a graphical representation of a differential equation. So it's a graphical representation of a differential equation. In the same way that our first solution or our first method was, but it's going to look slightly different, okay? So here we go. We have our dy dx is equal to cosine x. And what is dy dx? Yeah, I know you just said it. It's the slope, right? So dy dx is the slope. So what we're going to do is we are going to graph the slopes. So if we have our graph here, can you see that? Yeah, you can see that. Okay, and for a slope field, what you'll see is the slope field usually has these dots. So it'll have these dots where we put our little slopes. So it'll be like this, like that. And you'll notice if you printed it out for the examples, I gave you a worksheet for the notes so that it just has these little graphs with the dots on it. So it gives you a place to put your slopes, to graph your slopes. Okay, and then because dy dx is giving us the slope, we can say, and it's only dependent on the x variable, we're going to make a table. Okay, see that? A table with x and dy dx. So let's say I put 0 in for x. Cosine of 0 is, yeah, it's 1, right? So then we can graph that slope of 1. A slope of 1 means a rise of 1 and a run of 1, right? Which is about a 45-degree angle, right? A slope of 1. And because this doesn't depend on the y value at all, every time x is 0, doesn't matter what the y value is, your slope is still going to be 1. So you're going to graph this little tiny slope of 1. So just a little, like a little tangent slope. Okay. That's a slope of 1. Okay, now what happens, our next spot here would be pi over 2, right? For trig, anyway, pi over 2. For everything else, it's going to be integers like 1, 2, 3, -1, -2, -3. Okay, so for cosine of pi over 2, we know that one is, right, you got it, 0. And a slope of 0 is just, yeah, you got it, a horizontal line. So when x is pi over 2, we've got 0. Slope. And you can kind of see our slope field emerging now, right? And we're going to keep going. Again, at pi now, cosine of pi is -1. So we're just plugging that in. We get dy dx is -1. So -1 slope is going down, right? So a little tangent slope going down. And then the next one is 3 pi over 2. 3 pi over 2. And that one is 0 again, right? Cosine of 3 pi over 2 is 0. So plot the 0. And the last one, 2 pi. And we're back at 1 again. And you said, well, this doesn't look much like this, but it does, right? If you were to kind of connect these slopes, right, and draw a particular solution through here, we can do that, right? We would say, oh, we would just do the tangent slope. So my tangent slope is 1 there, and then it curls around, and it's 0 here as it passes through pi over 2. And then it's -1 here, and 0, and then +1. And you can see that sine, beautiful sine curve kind of emerge there into your slope field. And if you had a particular solution through one of these other points, you could still do the same thing, right? It would still emerge as that sine curve. This is y equals sine x. All right, That's the start of our subfields.